Alright, I'm taking another shot at trying to build a characteristic curve of this old Deming Marvelette pump. Last time I was trying to do both the pressure and the current reading with just this single channel logging multimeter. And I was thinking more about how I want to gather data simultaneously so that I can actually overlay the two curves and get them in the exact correlation to one another. And what I decided on is using this cheaper digital oscilloscope as a gateway to collect these analog inputs without having to get into building just some kind of basic ADC circuitry for like a Raspberry Pi kind of input or something. I realized that this scope does have a network connection available on the back, which I can then use Python, in this case in a Jupyter Notebook, to collect data at whatever interval I want. And then, so if I use just the two inputs on that I have hooked up to the oscilloscope, one of those is going to the pressure transducer that's meant for the multimeter, which is coming off of that fitting over there. And then the other input is the blue amp clamp here, which is a Hall effect sensor type. And it's really sensitive. I don't know. I just haven't used that enough to build as much confidence in it. So I wanted a second source of amp current draw information, and that's where I put the other amp clamp on there, which goes to the multimeter here, which can also be sampled in this case by USB. It's a USB serial infrared adapter that clips on the top of the multimeter. So with those three inputs, I would be able to characterize the behavior of the pump as the current, see how the current increases under the load of increasing pressure. And, mostly just out of curiosity, but also to see if I have this, tuned too high, or maybe my air precharge in the tank isn't right. I could use this information to potentially adjust a few parameters: the cut-in, cut-out pressures, the precharge in the tank, and I don't know, just general curiosity. So that's pretty much the setup. I'll trigger the pump on by running the pressure down, and then capture the curve of the samplings of a run from cut-in to cut-out, and then we'll talk through the code a little bit in case there's nothing magical here, but in case somebody else is looking for how to cobble together a similar setup, I'll talk a little more about the code and anything else that comes up. For the data capture, I'm using Jupyter Notebook so that I have a way to replay certain code as I want to adjust things and rerun without having to write a standalone script and command line interface. Additionally, this will give me an environment to visualize some of this data more easily. Some key libraries being used here. This is the library specific to the Rigol oscilloscope I'm using. I have a wired Ethernet connection to it where I put a small IPv4 subnet on the interface, and then the oscilloscope is configured with a static IP address on the other end of that point-to-point subnet. I'm using pandas to manage some of the data, particularly prior to visualizing. I'm using Plotly for graphing the data. And then to capture the data from the multimeter, I'm using this other package that is specific to this series of multimeters. No driver is needed. I am on Linux, so this is just a USB to serial FTDI chipset going to the multimeter, and then it has this infrared, transmit and receive for electrical isolation from the multimeter. On Mac, this would probably be exactly the same thing. On Windows, you might need a driver for the FTDI chipset in the cable assembly, which you can get from Fluke, or even a generic FTDI driver would probably cover it. So the first cell is setting up the oscilloscope, creating the instance of the object. I'm just doing a stop, setting my channel 1 and channel 2 scale, and then setting it back to run mode. That's mainly so that I can see that communication with the scope is working. If the channels were already set up this way, doing the stop and run, I can see that the light on the front turns red for a moment, but you can change the channel scales and everything on the fly. There's no need to stop it for this. Then for the multimeter, Right now this is being discovered as TTY USB 1, and then I'm initializing the start serial using, this is all on the module itself, so I'm importing the internal module called DMMutil as an object called Fluke here. And this tool would mainly be meant to be used as a command line, so that I dug in a little bit to find out what's inside. And based on the functions or methods that are used to make the command line work, I figured out the workflow to instead gather the data straight from elsewhere. I don't think I saw documentation about using the API directly for using the interface to the Python module directly. I just defined a function here to get the data out of both of these. This is specific to my application here. I did add exception handling around the Fluke call. There were a couple of cases where I was getting value error when something inside maybe had none. I don't know if it was failing to get a reading from the multimeter or if it was momentarily out of range or something. But I just put exception handling around that. The only time I think I saw a type error might have been when I hit Control-C or had to stop the capture and it failed somewhere in there. But I'm catching these exceptions because I don't want them to cause a crash while I'm in the middle of my data collection. And I haven't seen that. I'm losing significant data, especially I'm capturing between 5 and 10 samples per second. So losing 1 or 2 here and there is preferable to aiming for perfection and crashing the whole thing. And then the Rigol readings are a little more robust. It will return none if the readings are out of range of what is currently on the screen. So if the scale is not set correctly for channel 1 or channel 2, one of these will come back as none. Channel 1 is the current clamp. Channel 2 is the pressure transducer. So I'm passing none out if the measurement is none. Otherwise, I am doing the math here to multiply it into the values. The current clamp is 1 millivolt per 10 milliamps of current, and then the pressure transducer is 1 millivolt is 1 psi. So that's just getting straight multiplied by 1,000. I have just a little test here to read samples from all three. So we can see the Fluke reading on the AC amp clamp is 0.0. The current clamp on the scope is reading 0.475, and this is part of the reason I wanted 2 amp clamped inputs. Is I don't know if it just doesn't zero properly or if it is not calibrated in a more skewed manner, but I wanted to have the precision of this amp clamp and the accuracy of the Fluke one. And then the pressure transducer is currently reading 27 psi. I wanted the data collection to be such that I can start the loop. This will sit in a waiting state until the first non-zero value is read from the multimeter. It will then log data points roughly 5 to 10 times per second. It's a 100 millisecond sleep between iterations, but some of these actions take a little bit of time. So it ends up being between probably 5 and 8 or 7 and 10 readings per second. Each one has a timestamp, so I'm not relying on a regular interval to get this to graph properly. If there's a delay in certain iterations, it doesn't matter because I have the timestamp for each data point. And then the capture will automatically stop once it starts seeing zero readings. So once it has seen a non-zero reading, so it's captured data, and it has a good Fluke reading, it didn't happen to hit an error condition and get none. And if the Fluke reading is 0, it will then start counting 0 readings, and after it sees 0 5 times, it will then break out of the loop. All right, we're ready for data capture. I'm going to crack open that valve on the outlet hose, which just goes back to the supply tank, until we reach the cut-in pressure, and the capture is already running. So we're going to get a full cut-in to cut-out measurement. So we're just a couple psi above the cut-in pressure. We should reach it in a moment. I have pressure bleeding out the green hose there. The loop is running. I'm ready to look for that first non-zero current measurement. All right, I've got the hose turned off, so we'll be able to see in the data the low point in the pressure and figure out when the valve was closed and we started our full cycle. You can see the Fluke is saying 3.3 amps. And then if we look at the screen recording, we can see what data is coming in. This prints every 10 iterations, so we can kind of see status as we're going here. So we got the Fluke amperage at 3.3, scope amperage just a hair lower, and then the pressure coming from the scope is 29 psi, 30. This is effectively one data point being printed every second, maybe a little longer, so it looks like you're gaining a psi every 5 or 6 seconds maybe. So we'll let this run, we'll get a full capture cycle, and then plot this and see if anything interesting shows up. All right, we just cut off. The loop automatically stopped. Yep, the cell did finish running. So if we look at the data a little bit here, we have 2170 data points, and the first example looks like this. So we got a datetime object. Looks like our first one, we didn't get a reading from the Fluke. Let's take a look. Yeah, so the first one had some exception caught within the Fluke code. Scope amps, again, they have this weird offset of non-zero. If we go to like the middle, you can see that the scope amps actually are reading a little lower than the Fluke amps. So that's why I'm not, it must be a cheap clamp. I'm not entirely convinced about it. It is useful for being able to get very, like 20 megahertz resolution on other, on AC signals and other things that you're digging into, like, not just average smooth data points. But in this case, I think it's not. It's just a second data point. I trust the Fluke one more, but then again, the Fluke one also does not necessarily give the same level of resolution. So if we start looking at the data, I create a data frame out of the list of data points. I do have something in here that writes the data out, just so I don't risk losing it. I write it out to a file. The data frame at this point contains the timestamp, the Fluke amperage, the scope measured amperage, the scope's pressure reading, and then derived PSI per amp. The first data points and the last are all zeros, so of course that comes out to infinity. So I'm using Plotly to make a visualization of some of the data here. In this particular example, it was capturing the pressure and everything as it was decreasing, so you can see the pressure drop and then exactly where the cut-in was. So we can see the green line is the pressure. There's the open valve period here. Then we can see the both current readings show when the pump started, a couple second delay to when I close the valve, and then building pressure. So it looks like our cut in is around 27 psi, and our cut out is around 46. Interesting that we lost pressure data here. Cut out around 45.5. So both of those are a little higher than expected. I was expecting it to be set to a cut in closer to 20 and a cut out closer to 40. So that's one takeaway already. And then I have a second plot here. This is using that derived field where I tried to plot what I call efficiency, so it's PSI per amp. I plotted that, so that's the derived column in the data frame. I plotted that and scope pressure on the same chart. This didn't end up being that useful, but what was more interesting is instead of using the horizontal axis as the time stamp, having the horizontal axis be the pressure and the vertical axis be the different amperage readings. So this creates more of a characteristic curve type thing where we're saying how much current does this draw at a certain operating pressure. Other things I could look into with this are if I move the pressure tank precharge up from 30 to run in the 30 to 50 psi range, then I can look at whether the pump does better there. From what I found, we don't get more tank capacity out of the higher pressure range. It just makes the the outlet stream, a little more forceful, which might be useful for sprinklers or soaker hoses. But I don't really want to run this pump at a higher range than necessary, especially because we're already, going from 3.3 to 3.5 amps. The pump motor, I think, says it's rated for 3 amps full load amps. So it might already be, drawing a little more current due to its age and operating condition. And, I don't see any need to push an older pump like this higher and risk damaging it. So last night, when I first set this up, I did run one other capture of data. And when I graphed that data out, there was an interesting anomaly, like a jump discontinuity in this current versus pressure curve, where around the 44.5 psi mark, at those higher pressures, the motor was drawing more current. And this is the kind of jump discontinuity in a curve like this that I think can be informative for looking at a system like this. It's interesting that today's data didn't show this. I don't know if that's just because the water and the bladder in the tank were warmer and it was maybe a little more compliant up into this higher pressure, whereas last night the water was cold and maybe it escalated more quickly. Because this isn't time series data, I can't quite wrap my head around what factors might be involved that caused this last night but not today. But I thought it'd be an interesting example to show of the kinds of things that I'm looking for as I do some of these captures and plots. So that's all for this. I hope this is helpful for somebody who wants to look at using data collection from a couple different sources like this and being able to visualize the data. I know that for some people you might do this every day at work, but for others who are just trying to do some experiments like this, maybe seeing it all come together is a little more helpful. I don't think I'm going to post more about additional experiments in tuning, but I might, if I have a future video on this project, I might make mention of some of the things I found if I did repeat it. Thanks for watching.